Okay, go ahead. Go ahead, Musa.
Good afternoon, ladies and gentlemen. Let me start by thanking the organizers of this conference for making it possible for me to be in the United States of America once more. This is my third time of attending such a conference, and it has really been an eye-opener. Particularly grateful to David, a workaholic, who has kept the spirit of John Sheffield alight. I would also like to thank Bob for editing my paper and making it more readable. The first page there is simply the title, rather long. I think it should have been something like explanation of gravity. But whenever you mention the word gravity, it connotes force. Such an all-pervading force should have a simple and down-to-earth explanation. And this is what this paper tries to do, to give a simple and down-to-earth explanation of the force of gravity. Our starting point is this: if an electric charge is to assume any configuration at all, it is most likely to be a spherical shell of radius A with surface charge sigma per unit area.
Probably went backwards.
Backwards. The yellow thing there is supposed to represent a spherical shell of radius A with surface charge sigma. Such a charge will have a volume. This is a well-known formula for volume of a sphere. Such a charge will have intrinsic energy. This is also a well-known formula. Such a charge will also have mass. This formula for mass of an electric charge is not a well-known formula. According to this formula, the mass of an electric charge in the form of a spherical shell is proportional to the square of the charge, just like its energy, because there's a relationship between, a linear relationship between mass and energy. So you have a spherical shell like this. The force, the electrostatic force pulling the charge upwards will be balanced by the surface tension pulling the charge inwards to form a stable structure. Next, we have the equation for the electric field due to an isolated electric charge, the well-known Coulomb's law.
It's the bottom one.
If we have two electric charges, there should be an electrostatic force of attraction or repulsion between the two charges, as well as gravitational force of attraction. We can combine the two to give the force, the electrostatic force, the gravitational force, proportional to the product of the masses. If this is a mass M1, this is a mass M2, Newton's law gives the force of gravity between the masses. This is a charge Q, and this is a charge K. Coulomb's law give the force of attraction or repulsion between the charges. So the electrostatic force is put as plus or minus, and the gravitational force is always minus. Force of repulsion here is regarded as positive, and force of attraction as negative. This is just for two electric charges. What happens if we have a conglomeration of charges? If we have a conglomeration that is an assembly of charges, the plus and minus forces of attraction and repulsion will cancel out. But the gravitational force of attraction will add up. Say, for example, between me and Bob here, there is no electrostatic force of attraction or repulsion. Cancel out, exactly. But there is a force of gravity between us. If the force of, if the electrostatic forces do not cancel, I will explode like an atomic bomb. Thank God, they cancel out, exactly. So for neutral bodies, the electrostatic forces of attraction or repulsion cancel out. Therefore, a neutral body there is no electric field emanating from a neutral body. So there is no force, there is no electrostatic force between neutral bodies, but the gravitational forces exist. Of course, small as they may be, gravitational forces, but for massive bodies like the Earth or the Sun, they add up and become significant. So really, the defining equation is this one. Given the force of attraction or repulsion, plus or minus, between two electric charges, and the gravitational force, which is always attractive between two charges. If we replace these charges by massive bodies, neutral bodies, there will be no electrostatic forces between them, but there will be gravitational force. If this is a force, this becomes the electric field due to an electric charge Q. If there is no other charge, we simply have the field of an isolated electric charge. But the presence of a second charge alters the electric field from Q. If Q is a positive charge and K is another positive charge, how can we interpret this equation given the field between the two charges? If this is a positive charge and this is another positive charge, like charges, the field from the charge Q, we can assume on interacting with the charge K opens out a little bit, thereby reducing the force of repulsion between the charges. If Q is a positive charge and K is a negative charge, the interaction between the field from Q is such that it closes in a little bit, thereby increasing the force of attraction. So whenever you have charges, is such that the forces of repulsion are slightly reduced due to the interaction between the electric field from one charge onto another charge. The forces of attraction are increased. The overall result is increase in the force of attraction, the force of gravity while the electrostatic forces of attraction and repulsion cancel out. This, what we are proposing, as a cause of force of gravity. As I said earlier, between neutral bodies, no electrical forces, cancelling out exactly where the gravitational forces remain. Neutral bodies do not emit electric field. So we have bodies, massive bodies like the Earth, moving around the sun without any electrical radiation. Their orbits are closed. They move such that the change in potential energy is equal to the change in kinetic energy, and you have a closed elliptic orbit. If there were electrical forces between them, it will lead to some kind of radiation. But we don't see any radiation between neutral bodies moving around each other. I can move nearer. Now we go to conclusion. I really need to leave.
You can get, you want to get started? You gotta call the production team, huh? Where are they? No, that I can't help you.
Yeah, thank you. Can you have the lights? Conclusion. Electric fields emanate from matter. Electric fields emanating from matter crisscross space and balance out exactly everywhere, with electrical forces on bodies cancelling out, but the forces of gravity remaining. I have been asked since coming to this meeting whether I believed in the ether or not. It's not a question of believing in the ether. It's a question of what is your concept of space. Our concept of space is that it is empty, a vacuum with regions of matter. Matter emits electric fields. So electric field from a neutral body do exist in space, but the forces they exert on bodies cancel out. If the electric field balance out, the forces they exert will cancel out. So electric fields from neutral bodies exist in space, but in a balanced form. Light radiation is propagated along the electric fields. The concept of ether being a uniform medium filling space is untenable. If there is such a uniform medium, it has to fill the whole of infinite space. Nature is not so extravagant. Space is crisscrossed by electric fields emanating from matter and vanishing at infinity. That's what constitutes the medium through which electric fields, through which light is propagated. Number two, gravity is the result of the field from one charged particle being affected, bent, probably more or less in the same way as gravitational lengthening by the last speaker. This bending is such that forces of repulsion are reduced and forces of attraction increased. The overall result is force of gravity. Number 3, for better composed of equal amount of positive and negative electric charges, the strong electrical forces of repulsion and attraction cancel out, but the weak gravitational forces add up. This is really the main point of this paper. Mass of a body is a quantity that can be expressed in terms of amounts of electric charges constituting the body. So Newton's law of gravity can be expressed in terms of electric charges. It has been said many times in the course of this conference that electric charge is more fundamental than mass. As we have shown earlier, the mass of a body can be expressed in terms of electric charges. A corollary to this is, if mass is constant in accordance with relativity, then the charge of a particle does not change with its speed. If charge is constant, and mass can be expressed in terms of charge, doesn't it follow then that mass should also be independent of speed? Should. Gravitational force is a pulling force, not a pushing force, a pulling force. Why does one say that? If you have two bodies, imagine them to be the only bodies in the universe, there will still be force of gravity between them. But there is no other body pushing them inwards. Only the pull of one body against another. So, ladies and gentlemen, I thank you for sharing my thoughts. Every phenomena in nature has a physical explanation. That it has been said many times during the course of this conference. And every phenomena in nature has a mathematical expression, subject to human observation or experimental verification. I think I have heard this said many times during the course of this conference, and it made me happy really that I am among critical thinkers whom we share a lot in common. Thank you very much.
Okay, questions? Go ahead.
Not a question, but a comment. I don't know if you've ever looked at the electric universe theory, but what you're postulating there has a lot of similarities to something they're saying, where they look at the arrangement of atoms, and basically they believe that gravity is this very minuscule leftover residual electromagnetic force that's so much less than the true electromagnetic force, but they think that they agree that gravity is an electromagnetic manifestation, but a very much lower level.
Thank you. Yes, sir.
When you did your derivation of the electric force between two bodies, you did the Coulomb static force.
Yes.
But there's a velocity term also, and you didn't include that. And that would cause you to have a net attractive force between vibrating neutral electric dipoles. And all atoms have electrons and protons in them, and they vibrate. And you should try learning how to do that calculation, because it never averages to zero. It's always attractive. And it goes as V over C squared. That's why it's 10 to the minus 39th power as strong as the electric force.
Minus 39.
10 to the minus 39th power as strong as the electric
Certainly,
force.
one cannot say that that equation of electrostatic and magnetic force is electrical. There are other effects.
It is electrical.
Well,
It's not a static force. It's
Sorry, yes.
It's not a static force, it's an electrical force. See, electrodynamics in Maxwell's equations includes velocity terms. You haven't included any velocity terms in your work.
Well, I am here talking of charges at rest.
And the other thing is, but charges are never at rest. Nothing in the universe is at rest.
Of
Everything
course,
is moving.
certainly. You are
And,
right.
but the other thing is, you assume a sphere of static charge. And there is no evidence that any elementary particle is a sphere. There's no evidence that any elementary particle, electron, proton, or any particle is a sphere. All particles have a definite shape and size. For instance, the proton and the electron have a spin, and they have a magnetic moment. You cannot explain that with a sphere. You can measure it though.
Yes.
So it's explained by a different shape. And in the work that I did, where I derived the radiation reaction term, I derived it from the empirical equations of electrodynamics. The reason, what you discover is you have a boundary condition that you must satisfy, and the only way to satisfy it, to get one of the three terms to be the only term that you derive, is if the shape of the building block of all elementary particles is a toroidal ring. It has that periodic structure. It has both a magnetic moment and a spin. And you haven't looked into those things, and you need to.
Thank you
Just a
very
basic
much.
book on electrodynamics,
We'll certainly do so.
like Jackson's book, will tell you how to derive it.
Okay, thank you. Thank you for that comment. Any more questions? Once more, thank you very much.
Okay, thank you.